Hello YouTube, welcome to 2016 AB1. Well, it's also BC1. Re-recorded. We already did the TI-83 version. This will be the TI nSpire version. All right, number one says, water is pumped into a tank at a rate modeled by WT is given. That function is given in liters per hour for T between 0 and 8, inclusive where T is measured in hours. Water is removed from the tank at a rate modeled by R of T liters per hour, where R is differentiable and decreasing from 0 to 8, inclusive for T. Selected values of R of T are shown in the table above. At time T equals 0, there's 50,000 liters of water in the tank. Part A. Estimate R prime of 2, show the work that leads to your answer, indicate units of measure. Okay. All right, so this is AB1, BC1. Part A. Now, R prime of 2, we really can't get because we don't have R as a function. But we have R of 1 and R of 3. So let's estimate the slope of the tangent line, R prime of 2, with the slope of the secant line with the average rate of change from 1 to 3. So delta R would be 950 minus 1190, in other words, R of 3 minus R of 1, over 3 minus 1. Oh, okay, let's do that. All right, so let's see. It's going to be an estimate, right, of R of 3 minus R of 1 over 3 minus 1. And R of 3 was 950 minus 1190 over 3 minus 1, which is 2. And the numerator is negative 240, is it not? Yes, it is. So you got negative 240 over, negative 240 over 2 is negative 120. Now remember that the R is given in liters per hour, and so the delta R's are in liters per hour, and the delta T's in the bottom are in hours. So this is in liters per hour, or liters per hour squared, if you like some people say, instead of meters per second for acceleration, they say meters per second squared. And just for fun, let's do that on the calculator. Let's bring out a TI nSpire CX CAS emulator. There you go. Sort of silly to do arithmetic on here, but just to bring in the calculator, bring in the big guns. Here we go. All right, so reading off the table, R of 3 minus R of 1 over 3 minus 1. Let's do it. Let's get a document. Let's do a calculator document. Let's do control divide for big fraction. And what was it now? It was 950 minus 1190. 1190 over 3 minus 1 is negative 120. Wow, that was earth-shattering. There you go. All right, 1B. Use a left Riemann sum with 4 subintervals as indicated by the table to estimate the amount of water removed. Remember, R of T is how much water is being removed, and W of T is how much water is being pumped in to the tank, right? From the tank during these 8 hours. Is this an overestimate or underestimate of the total amount of water removed? Give a reason for your answer. Okay. All right, so I'm going to graph these values, okay? Let's see, I think, so R of 0 is 1340, R of 1 is 1190, R of 3 is 950, R of 6 is 740, and R of 8 is 700. But I don't think I need to do that what do they want? A left Riemann sum? I don't think I need R of 8 to do this, but there you go. All right, so let's just graph it just to see what's going on. 1B, I like to visualize this stuff, okay? Whoops. So, let's say, okay, we're going up to at most 1340, right? So let's say this is 500, this is 1000, this is 1500, this is R. Just roughly, just to get an idea of what it looks like. And there's 0, right? And that's R. And this is the T axis, and we're going from 0 to 8, right? So they give you R of 0, R of 1, R of 3, R of 6, and R of 8, okay? All right, now R of 0 was about 1340. Let's say that's here. All right, so I'm going to draw, say that high, roughly, right? R of 1 was 1190. Let's say that's this high. Okay, roughly. R of 3 is 950. Let's say that's this high. Oh, wait, I did it wrong. Okay. I got to go. I know R of 1, but I don't know R of 2. So let's go up to R of 3. Go on, R of 3 is 1190. Let's say that's 1190. And then R of 3 is 950, so let's take this side up to like 950-ish, would say here. Okay, there you go. And then 700 for R of 8, let's say that's here. Whoops. And if we're doing a left Riemann sum, I don't really need f of b, do I? F of 8 is f of b. I'm not getting this piece. There you go. All right, so I need the rectangle whose base is 0 to 1. Let's say rectangle 1. A rectangle 2 from a base of x equals 1 to x equals 3. Rectangle 3 with a base of x equals 3 to x equals 6. And rectangle 4. Using the left side heights, right? So the integral from 0 to 8 of r of t, which is the rate of change already in liters per hour. All right, so we got liters per hour times dt is in hours. You're going to get a total number of liters of water that was lost. We're approximating this with the first rectangle's delta x, or base, is 1, and its height is 1340, plus the next delta x from 1 to 3 is 2. That's the base of the rectangle. The height was 1190, plus the next delta x from 3 to 6 is 3, times the height at r of 3 is 950, and again this is just an estimate, and from 6 to 8 delta x is 2 and r of 6 was 740. And let's work this out. So what do we get? All right, that's what the calculator's for. All right, calculator work. There you go. Okay, so let's do that. It's going to be 1 times 1340. Oops, no, not that. No. Back to my 1. Stop it. 1 times 1340 plus 2 times 1190. Stop it. Oh boy. Sorry, my SmartBoard is sticky. Okay. Plus 3 times 950 plus 2 times what was it, 740 is 8,050, and we said it was liters, right? So let's say that's 8,050 liters. Okay. Now, is that an overestimate or underestimate? Well, it says that our selected values R of t are shown in the table of at time t equals 0, there's 50,000 liters of water in the tank, blah, 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 where R is differentiable and decreasing. Aha. So, if you have a decreasing function, L sum is going to be an overestimate, isn't it? Yes, it is. Okay, so this is an overestimate. Whoops. L sum is an overestimate because f prime is negative. In other words, the function is decreasing. Ta-da. All right, so that's 1b. Alrighty, 1c. Use your answer for part B to find an estimate of the total amount of water in a tank to the nearest liter at the end of 8 hours. Well, remember, at t equals 0, we have 50,000 liters of water. And during that 8-hour period, we just had an overestimate to how much water was lost based on R of t, was 8,050 gallons. So we're going to subtract that from the 50,000. But then are we going to add up all the water that's pumped in? Okay, so let's write that down. 1c. Isn't the total amount of water going to be about the amount of water you started with minus the 8,050 we just got, plus the definite integral from 0 to 8 hours of Wt, which is 2,000 e to the negative t squared over 20 dt. So let's work this out on the calculator and see what we get. Okay, so it's going to be 50,000 minus that answer. Whoops. Sorry, my thing got stuck here. Minus that answer plus the integral. Let's see, how about a definite integral like this one? From 0 to 8 under the function for the function, well, this is now 2,000 e to the negative t squared over 20 that's sort of hard to read. That's correct. But you could do this instead of limit. There you go. Give me a rational. Negative t squared over 20. I'm doing this with respect to t, right? And they want this to the nearest liter, so that's 49,786 liters. So let's write that down. 49,786 liters, approximately. Okay. Alrighty, now. Alright, so part D, what do we got? For t equals 0 to 8 inclusive hours, I guess, is there a time t when the rate at which the water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. Alright, so 1D, huh? Let's see, 1D. Don't you want to know when W of t is equal to R of t, right? That's what they want? Is there a time such that Wt is equal to R of t between 0 and 8 for t, right? Inclusive. But doesn't that mean that this has to be 0 at some point? Now they're saying that W is differentiable and R is differentiable, right? And therefore they're both continuous. And so the IVT comes into play, the intermediate value theorem. For example, say that the maximum value of W minus R is 1,000, and the minimum value of W minus R is negative 500. Don't you have to have 0 in there somewhere? Yeah, you do, right? So what is R max? Let's talk about this. What's R max? What's W max? Okay, let's go back to the question. All right, W max. How did I do this? Okay, all right, so here we go. R, now they're decreasing, right? So R max is R of 0 is 1340. R min is R of 8 is 700 liters per hour, right? What are W max? So that's W. That's R. Now what's W max and what's W min? Well, W max, again, would be if you plug in 0, right, into W of t. Isn't that 2,000? And W min is going to be W of 8. Because, again, they're decreasing, right? So, let's see. Let's talk about this. So, W max is W of 0. But W of 0 is 2,000. Okay. W min is W of 8. What is that? Let's break out the calculator. Okay, calculator. I need 2,000 e to the negative 8 squared over 20, right? So it's 2,000, whoops, e to the negative, well, 64 over 20. Why is this getting stuck again? 20. Well, give me a decimal. It's 81.524 something. 81.524 something. Okay. Now, R max was R of 0 from the table. R of 0 is 1340. And R min on the table was R of 8 is 700. So, what's the maximum value of W minus R? Isn't that 2,000? In other words, W minus R has got to be between W max minus R max, which is 660, and the 2,000 minus 1340, And W min minus R min is going to be 81.524 minus 700, which is negative 618.476. So by the intermediate value theorem, there must exist at least one value of t on the interval from 0 to 8 such that W minus R is equal to 0. In other words, there must be a t such that W equals R. W equals R of t. Okay, there you go. That's it. Done. All right, hope that was helpful. Bye-bye, YouTube.